So I know what some of you might be thinking. You might be sitting here thinking, I'm at Discovery Day and my sole goal is, where's the best place for mineral exploration? Where can I find the next Olympic dam? And then if that's your chain of thought, then you might think, well, why should I care about the AusLAMP models? I mean, if we're being realistic, the resolution of those doesn't start until 10 kilometres beneath the surface. And the mineral deposits that you're all looking for are within the top 500 metres or less. So why should you care? Because it was MT that found Olympic Dam. Okay, it didn't find it first, but the models do find it. And you can see that there's this lower crustal conductor and it points straight up to Olympic Dam. And then what about the conductors on either side? I mean, they don't point to Olympic Dam. Well, no, they don't, but they do point to Well and Vulcan, two other IOCG deposits in the Olympic domain. So then maybe you're wondering if this is an isolated occurrence, and it's certainly not. This is occurring across the globe, and I'll show you a couple of examples of that shortly. We also have these transects where we have conductive pathways and they lead up to the surface and there's no mine above it, and perhaps there's no mineral deposit. Or maybe there is, and maybe these pathways are pointing straight to a mineral deposit that are waiting to be found. So I'll take a step back now and just explain to you why we see correlations of anomalous conductivity structures and mineral systems. So the figures here are from a recent paper published in Nature Communications. And the paper gives direct evidence, the first direct evidence for gold coming from the mantle. So you can see in the figure on the left, gold in the mantle mineral structure. And this was sourced from mantle that was directly beneath a large gold province within the crust. The paper then goes on to talk about what you need to form a gold deposit in the crust, and these can be applied much more generally. And this has been covered a few times already this morning. But you need three things. So the first is that you need an enriched crustal or mantle source. And this could come from perhaps metasomatism from a plume event, for example. Then you need to mobilise the enriched region. So this could come from a subducting plate, which you can see in the bottom figure there, which releases fluids. And then you've got enriched fluids or partial melt. They're stuck in the mantle. How do you get them up to the crust? And that's these all-important lithospheric structures. And these lithospheric structures tend to be craton margins or just the boundaries around lithospheric domains in general. This is why it's so important that we can image where these are. And if we head to the western United States, the red circle near the top is around Yellowstone, to give you an idea of where we are. And this map's showing seismic velocities from P-wave seismic velocities from seismic tomography, and we're at a depth of 90 kilometres. The blue regions are low velocity, and the mineral deposits are plotted with the circles, and the yellow dashed lines are outlining lithospheric domains. You can see that these tend to cluster on the low velocity regions or on the gradients where we're going from low velocity to high velocity and correlating with the lithospheric domain boundaries. Then moving to South Africa, and this time we're plotting the locations of kimberlites, and we're over resistivity, where the red to yellow regions are conductive and the blue regions are resistive. And the kimberlites we're interested in here are the red ones. These are the diamondiferous kimberlites. And there's a really good correlation here. I should mention we're at 200 kilometres depth for this slice. There's a good correlation between the gradient from really resistive to really conductive within the Cupvale craton there, but you also see it in other areas across this model. What you can see is that the red dots, the diamondiferous kimberlites, aren't on the craton margin, which I've very badly drawn in blue there, but it's more on the margin of where you're going from the sort of the resistive core of the craton into the more conductive exterior. And that's very similar to what we see in the Gawler craton, where we've got the really resistive core, and then we're still in the Gawler craton, but we've got the conductive margin around it, and I'll show you that in more detail in the next slide. What I've plotted here is resistivity at 30 kilometres, where the red regions are conductive and the blue are resistive. And I've plotted the locations of mines with the green dots and diamond occurrences with the yellow diamonds. And there's a really good correlation where these are occurring, again, from the conductive anomalies and when we're moving back into sort of the more kind of background resistive signature around. And the exception to that is the kimberlites, where most are occurring on the boundary, particularly around the Gawler Craton, but then you've got a couple of clusters in the Flinders Ranges where they're on that conductive, the conductive anomalies there. So sort of the lower 2/3 of this is the model that you were just looking at, and then in the top right-hand corner is the new Pace Copper funded Northeast AusLAMP data. So this is the first time anyone would have seen these results, except for all the people crowded around Stephan just moments ago. But basically, so I just want to talk you over the state as a whole and what new things we've learnt from the new data. And some of you also might not have seen the Kumpana province data in the far west. So that's where I'll start, in the Kumpana province, where the conductivity is relatively homogeneous and it's sort of moderately conductive. We'll move over to the east into the Gawler Craton, which I've already briefly talked about. And we've got this really resistive cratonic core. And this is typical of a depleted region. Around that, we've got the conductive margin. And then we're still within the Gawler Craton, but it's going back to resistive. Then into the Flinders Ranges, we've got these conductors, and these extend down into the mantle, and that's where we were seeing the kimberlites. The Kernamona province, Graham will speak to you about that in more detail at the end of this session, but that's really conductive throughout a lot of the crust. And then we move to the new data, the northeast model. So these are two different models kind of just pasted together, but you can see at the boundary that there's really good correlation of the features. So when we're looking in the northeast of the Gawler Craton, one thing that we see differently here is where we thought that the conductive margin just sort of went immediately around the Gawler conductive core, resistive core, sorry. It's actually starting to fork off into two directions, which you can see here, where there's an arrow going up, heading up towards the Musgrave province. So we don't actually have any data in that region yet, in the eastern APY lands, but it'll be interesting to see what happens with that trend there. Over in the far west, in the western APY lands, we have just recently finished processing that data, but it hasn't yet been incorporated into any of the models. And I'll just have to go backwards here. Another feature that we see from this northeast data is once we go north of the Gawler Craton, and so anywhere kind of west of that pink line that's drawn there, it's still really resistive. It seems like we're still either in the Gawler Craton or just some sort of region that's cratonic-like, resistive, depleted. Once we go to the east of that line, that's where we're in much more conductive mantle, and that might be where we're transitioning into more Phanerozoic mantle, perhaps. So this region in the yellow is where I'm going to just show you the model briefly in 3D. Before I press play, what we have here is a transect down to 300 kilometres, where again blue are resistive, green are conductive, and it's from the southwest to the northeast across there. What the first arrow on the left's pointing to is the resistive Gawler Craton. The second arrow is pointing to the conductive margin of that resistive core. And you can see that that's mainly in the crust, but there is a connection down to the mantle, and that connects to a much bigger structure within the Gawler Craton, in the northern Gawler Craton. Then we go back into resistive. We're still in the Gawler Craton mantle here. Then where that dashed line is, you can see there's a stark contrast, and we're into what may be the Phanerozoic mantle there. So just press play. And we'll just zoom in, and you can see the crustal conductor of the Gawler margin in more detail. Then we'll turn on the iso surfaces. So the blue are resistive, the green's really conductive, and the mint is sort of somewhere in between. And you can see that curved shape of the Gawler margin there in the more resistive core. Now if we spin around from the east, you can see that it's the conductor in the mantle And that's the sort of the Phanerozoic type part, perhaps. And then from the west, we've got the resistive Gawler craton. If we turn those off, you can again see that conductive margin of the Gawler. You can see it in 3D there and how it's extending down into the mantle. And again, it's really conductive on the eastern part of this model. So you've seen how we've got correlations of resistivity structures and mineral deposits. And you've seen the new models in 3D, but what do they look like when we're looking at a vertical slice? So both of these slices are taken from AusLAMP models. And I should mention, for those of you who don't know, AusLAMP long period MT data, so it's really deep sounding. It's a period range of 10 to 10,000 seconds, which means we can image several hundred kilometres deep, but our resolution doesn't really start till 10 kilometres, as I said. So what you can see is we've got the conductive pathway, and it's mainly within the crust in this top model. And it's actually quite similar in appearance to what we've seen in the Kernamona province a couple of years ago. But one thing that you do see is that it's hard to sort of see what's happening when you get near the crust. It's a very wide conductor, and we're losing a lot of resolution. So then if you did a much higher resolution survey across the area, would you resolve these features in the crust? And I think from my first slide, you should know the answer to that is yes. And these are two broadband MT transects that mainly focus on the crust. The bottom one is collected across Olympic Dam, which you've seen, and then the top one is across the Beverley uranium mine. So we've got a conductor that's leading up, pointing straight to the uranium mine. And these fluids actually didn't bring the uranium, but they did provide the redox conditions required to precipitate out the uranium here. So then if we know that AusLAMP can image these fluid pathways, and we know that broadband MT can image them even clearer in the crust, then the obvious progression from here is to do infill surveys from the AusLAMP, target particular regions of interest. And that's what we've been doing. So we've done, well, Ben at Adelaide Uni, and Graham will talk about this more, has done an infill survey across the Kernamona province, right across that conductor there. So I'll show you that model on the next slide. Just kidding, Graham. Then on the right-hand side of the screen is infill array across Carapatina and a few other deposits there. And what it's plotted over is a 10-kilometre resistivity slice from AusLAMP, and you can see that these deposits are all right on the edge of this conductive to resistive transition there. So here we're collecting 320 broadband MT sites and AMT sites, and flying 3-kilometre line-spaced AEM. So stay tuned for the results of that. I'm sure they'll be fascinating. And I'm just going to end with a bit of a video on what AusLAMP is. Sorry, my video is not quite as flashy as Richard's, but and I don't want you to take away just the pretty pictures from this, so I just want to go over my key messages one more time. And that is that the deposits are controlled by the lithospheric architecture. And that you have to remember that the mineral system is more than just several kilometres beneath the deposit. It includes the entire lithosphere. MT is a perfect tool for imaging this lithospheric architecture, and that makes it a great exploration tool from a regional scale to a camp scale. Thanks.